So yeah, so we remember this guy from last week and last 2 weeks, and we remember the fact that we've got the ALU, and then we've got the general purpose registers, and then we've got the ALU. Beneath the ALU, we've got the SRAM. So we've got the SRAM is RAM, random access memory. That means it's volatile, right? So far we've dealt with the input and output, and you have also, I've shown you a bit about UART, register manipulation, some stuff about instructions and other things. So talking about RAM, what happens and how do we work with RAM? So somewhere in there you will get information about SRAM if I can find it in the right path. Otherwise, I will just jump into it and then we'll start talking about it somehow. You can simply do SRAM search. I'll find it for you later because we are pressed by time. So let's do a quick talk over it. Varun, I was expecting a reply from you. Are you okay with the whiteboard now? If it is so difficult to follow, let me know. Otherwise, I'm jumping right back into the whiteboard. Okay, so right back into the whiteboard. Nothing's been said so far. Right. So we know the SRAM is the volatile memory. Non-volatile means that if you switch off the power, you still get your data being stored for you. So examples of non-volatile memory, we've got something like flash, hard drive. So you've got something like flash, and also a bit more, but we can actually, as far as the 18 mega 32 AP are concerned, remember when I was explaining the architecture, I emphasized on the flash and the ROM. So on the 18 mega 32 AP, the flash and ROM are non-volatile. And then we've got the volatile memory. So I'll say VM, and the volatile memory, you have the SRAM. So when you switch the power, you lose the data in the SRAM. And then the registers, right? So we've got the SRAM and the registers. So non-volatile, flash, EEPROM, volatile, you've got the SRAM and the registers. Okay, so now we want to take a closer look at the SRAM. So when we write our code, remember we mentioned before, looking at the architecture, that obviously code sits in memory and then the processor executes, fetch and execute the code from memory, right? So if this is our SRAM, static RAM, right? So you can have SDRAM, synchronous data RAM, DDR, double data rate, all those kind of versions that, but I believe you can read those stuff from the internet and understand them. But when it comes to dealing with things from low level, this is what we need to find out. So when we have a variable declared, let's say int var, or let's make it simple, right? Let's say if you declare a variable my int. So we have a global variable called my int. So we have my int. If we say int my int, and then if we say int x equals 5. Now these two are all declared as global variables. So outside the setup or outside the loop, or now we know outside the main, right? So these global variables, they are different. Well, obviously two different global variables of the same data type, right? Int. Now int is what, 16 bytes. So we've got 16 bits of integer data. Okay, all right. Now, or two bytes, which reflecting back to earlier weeks what we did. We declare my int, but we have not initialized my int. and then we declare X, but we have initialized X. So within the memory, if we can just create our imaginary divide, right? If we create an imaginary divide, we've got the dot data, just the name we are assigning to a group of 1, 0, 0. And then we've got the dot BSS part of the memory. Now, the dot data is where we will store all the variables that have been initialized. So even though we declared an initialize X after myInt, X will appear in this bit of memory. So we put the value 5 will appear in this memory. So it wouldn't be X, of course, it will be binary representation of 5. And then myInt will appear in the .bss part because X, so the dot data part is the ones that has been initialized. Let's use init for that, right? And then the ones that have not been initialized, the ones that have not been initialized will go to the .bss. So on init or unit. Still splitting the RAM. Now, if we were to jump back and forth in the data sheet, you will notice that the memory, the address location of the SRAM in memory, the SRAM starts from register location 100 or register location 100 in terms of hexadecimal. You can put 0 in front of it. So 100. All the way, we have 2 KB of memory, so you can actually do the conversion yourself. So 2 kilobytes of SRAM. That takes us to 0FF. So this is the first address of the SRAM, and this is the last address of the SRAM. And the way the SRAM is organized, you have the initialized data and then the uninitialized data going to the WSS session. Now we have something called the stack, right? And an example that we use the stack to actually represent a stack is, let's say if you have a stack of coins, the first one you put down on the table will go to the bottom, and then the last one will be on top. So we say we push onto the stack, and when you are taking data out, you pop out of the stack. So the first one is at the bottom and the last one is at the top, and then so vice versa. When do we use the stack? When we need to do a jump statement, we save all our variables into the stack. So things like functions, right? So if you have a function or if you have an interrupt, all the local variables that are all the variables that are local to this and all the variables local to that will go into the stack, or all the variables that need to be saved will be pushed onto the stack. Okay, so the stack is at the bottom. So we can say at the bottom we have the stack. So variables that are local to function calls and interrupts and other things will go into the stack. Okay, good. Now what that means is that when you write your code, if you do not optimize your code well, let's say variables that are local to functions or subroutines, right? So you just say subroutines, sub R, or interrupts. Okay, now if you do not organize your code well, or if you do not optimize your code, somebody was asking about what was the whole point of memory optimization. If you do not optimize your code well, you may have your stack growing up because it grows from a lower address towards a bigger address towards a smaller address, so the stack actually grows as if it's growing younger, whilst the BSS and the data also growing down. If you are not careful, you have the stack and the BSS also overlapping each other, and that is when you have some gibberish representation of data, or data not looking as expected. Now I've just skipped one step, as if this between the stack and the BSS we have nothing, but in between here we have the heap. So the heap is for dynamic allocation of memory. So if you dynamically allocate variables, which means if you are not sure, if running of your program, if you are not sure whether, let's say, you are going to need a variable or whether the variable is going to be what type or anything, you're just not sure. During runtime, you can use something like the malloc function to memory allocate, to dynamically allocate memory in the heap. So once you actually make a lot of use of malloc, you can have your heap growing so fast and meeting your stack, which can cause invalid data.